Okay, so in this video, we are going to determine all of the octahedral isomers of the form MA2B2CD, where M is a generic central atom, but typically a transition metal, right? And A, B, C, and D are four different chemically unique monodentate ligands. And we're also going to determine the chirality of these species. Some of them might be chiral, some of them might not be. Okay, so the way that we've been doing these in these videos is a very systematic way. So we keep track of the trans pairs. So we have three pairs of ligands, right? Because we have six ligands total. And the best way to do this is to do it in a very alphabetical manner to make sure that we don't repeat or miss any of the isomers. And so the most alphabetical way to list this at first is to have A and A together, right? And then after that, we used up the A, so the next most alphabetical way is BB, and then CD. And so that's going to be our first structure here. We can then go AA again, and this time, instead of BB, next in line would be BC, right? And so that forces this to be BD, and that's different, a different set of three pairs. So as long as we have a different set of three pairs there, we have a unique structure. Once we've done this, we can think about, can we do anything deeper with the AAs alphabetically? We've done BC, so next would be something with a C. We're not going to do CA. Our rule here is that we're never going to have an individual pair that's in reverse alphabetical order. So we never list it as CA. Instead, we'd list it as AC. Now, in this case, we can't even do either of them because we only have three A's. But that's just an idea. We think to ourselves, do we have CA? We don't. So next, CB, we would not be able to do that either, right? Because that's, again, we would list that as BC. That's the correct way to list this to avoid redundancy. And we've already done BC. We can't do CC because we only have one C, but we can do CD. That forces the third pair to be BB. Well, that's the exact same as what we have listed as our first structure, except in a different order. So that's redundant, so we'll just cross that one off. Now that we've done AACD, the next could be, we could consider as AADB or AADC, but those, again, are reverse alphabetical order for that one that started with D, so we're not even going to do that. So this tells us that we're done with AA, and we have to move on to the next alphabetical ones, which are AB. Most alphabetical way to do that is to have another AB and then followed by CD, and that's a unique structure. We can try AB, AC, and that forces this to be BD. That's valid. We can also think about AB, AD, BC, and that's also unique. And from here, we can try other AB structures. We're done with AB, AC, AD, so we're done with that. So next would be BC. Well, that gets us back to AD. That's just what we did up above. So it's redundant. A, B, C, D would be next, which is A, B. That gets us up here, same one. So we've done that. So we're done with the ABs. Now we move on to the AC. If we do AC, next alphabetical order would be AB. And then that would force us to have BD here. But we already have that here, just the A and C and the AB flipped. And so we could do AC. We can't do AC again, but we could do AD. The reason why we can't do AC again is because we only have one C, and that would force this to be BB. And that is actually a unique structure. So we're at six structures at this point. This turns out to be all the structures that exist, but we can go through and check to make sure that we're not missing any. And the way to do that is just keep plowing ahead with this alphabetical business. So 80, our A's are done here for AC. So now BA, no, that's the wrong way. So we'd have to do BB. Well, that gets us AD. So we did that. AC, BD would be next. And that was AB, that's right here. Or right up here, not crossed out. Okay, and so we've done now all the ACs. We can try the AD. First would be AB, but that is BC here, and so that's right there. We've already done this. So I'm just kind of blasting through this because I know these are redundant. AD, AC, BC. Um, that's let's see, an 80, sorry, 80 BB. We can't have two C's. That one is right there. That's redundant. And now, what other ones do we have left? We're done with AD almost. We have to do AD, BC, and AB, right? And so, if we do that, we are now, that one is also redundant. And so if you look at this carefully now, we've done most of these, but the ones that are not redundant, you never have a flipping of the trans pairs in alphabetical order. So you can see this one, AABBCD, is the first time we listed it. That's good. Here we have AABCBD. It's going in this pair is number one ranking alphabetically, then two, then three. One, these are tied for one, and then two, right? One, two, three. Once you start getting redundancies, they flip in the ranking. So this gets you one, three, two, right? So that means it's redundant. This one was one, two, three. That's not redundant. Okay, so that's another way that you can test this. But I like just, you really want to make sure you get the problem right. I like just going through. Sometimes you will miss ones if you're not, super careful. Uh, so we did A, D, B, C. That brings us now that ADs are done. So there's no BA, but there's BBs, right? So BBAA, that forces us to do CD. That's what we just had here. BBAC, and this would be AD. We had that down there. BBAD, after AC, AC, that's just what we wrote. And then we could do BB, CDAA. That's the first one written in a different way. So we're done with BBs. Now we're BCAA, BD. That's our second one. So that's redundant right there. And BCABAD. That's this one right here. And BC. We can't do a C, so A, D, A, B. We just wrote that one. That's done. And then lastly, we could do B, C, B, D, A, A. That's our second one written in a different way. And very last one, we have a C, D, A, B, B. That's our first one written in a different way. And C, D, A, B, A, B. It's our only other one, and that's that. So again, we have these six structures. So now we can finally write them out. Let's give them labels here. Let's call it 1, 2, 3, 4, 5, 6. And this part, writing them out is the easy part. Put the metal in the center. AA are trans from one another. Remember, these are trans pairs. So I put them top and bottom. You could put them, coming out this way and that way. It doesn't really matter as long as you have the trans pairs correctly. So B and B are across from one another. So this is coming out towards us to the right. That's what the wedge means. The dash means it's going behind us to the left. And this dash is going to be C and D. So again, I could have scrambled the orientation of these in terms, as long as I have A and A across from one another, B and B across from one another, C and D across from one another, I'm good. That would just be viewing the same structure from a different orientation if I drew it a different way. So that's structure one. Structure two, same sort of thing. Here it is. I have AA that is trans from one another, BC, and BD. All right, number three, I have AB and another AB. Okay. And I'm actually going to draw this a little differently because when we look for mirror planes, it'll be a little easier to see if I draw it this way, but just easier for me to draw in 2 dimensions. So I put AB, AB, and then C and D I'm going to put on the top there. 4, I have AB transfer one another. I have A and C transfer one another. And I have B and D transfer one another. And I also have structure 5, which is very similar. It's going to be A and B transfer one another, A and D, B and C. And structure 6 is A and C and A and D and B and B. Okay, so last thing we can ask, so at this point, we have figured out that we have 6 unique stereoisomers. And last thing we can ask is about chirality. Okay? So for chirality, you're going to be looking for mirror planes. If you can find a mirror plane in your molecule, doesn't matter what the molecule is, then it's not chiral. Okay? Chiral molecule cannot have the mirror plane. So there's a mirror plane in structure 1 here that contains M, B, D, C, and B. That's one of the mirror planes. There's actually 2 mirror planes in this molecule. But this mirror plane, A is looking at A in the mirror plane. So mirror planes like this, the horizontal mirror plane coming out of the screen, and then we have A on top and A on bottom. So A is looking at itself in the mirror plane. So if you do this symmetry operation, A would turn into another A, okay? And so nothing overall would happen to the structure of the molecule. So that tells you have a mirror plane. So this is not chiral, or another word for that is achiral. The A prefix just meaning not chiral, okay? Same idea with structure 2. We have that horizontal mirror plane with A and A. And so because we have a mirror plane, we are not chiral. Structure 3, there's also a mirror plane, but the mirror plane is a little bit different. We don't have A and A trans to one another or B and B trans to one another, but instead we have an A and B cis and an A and B cis. And so we can draw a mirror plane that cuts, it's just going to contain C, M, and D, and the A here is in front. Sorry, I drew that a little strange. Let me try to draw that again. It's going to contain C, this is a better way of drawing it, M, and D. Just like that. It's cutting between the B's and between the A's. So it contains C, M, and D. Okay, it's coming out like this. And the A on the right is looking at the A on the left. And the B on the left in the back is looking at the B on the right. So they're looking at each other in the mirror. So again, when you do this operation, nothing happens. So this has a mirror plane. So again, because it has a mirror plane, this is achiral, not chiral. Structure 4, you can look at this for a while, but actually doesn't have a mirror plane. We have these cis A's and cis B's, but they're not in the same square like that. So that one's going to have a left-handed and a right-handed version. And we can actually write the other version if we want. So this is sort of our mirror plane now here, and we could draw that structure. So we're flipping it like that, okay? MAB are D and C are going to switch positions when we do this. Oh, we'd have it like that. Okay, so we'd have now the left-handed, right-handed enantiomers of this. Structure 5 is also chiral. Similar thing. We have the A's cis to one another 90 degrees apart, and the B's 90 degrees apart cis to one another, but they're not in a square plane. They're not trans to one another. So that's chiral. And again, we could draw a mirror plane here and draw the other handedness. So I'm going to do A and B. And I'm going to flip, instead of having B and A on this side, I'm going to have D and C and B and A. C, last one to consider, has a mirror plane. And the mirror plane, because B and B are trans to one another, so they're across from one another, so the mirror plane is going to, see if I can draw it, is going to contain M, C, A, and A, and then the B's are looking at each other. One B's, so the mirror plane is like this, one B's over here, one B's over there, and they're looking at each other. And so that is achiral. It's not chiral. And so at the end of the day, our final answer in terms of the number of isomers would be, hey, we have 6 stereoisomers with two of them are chiral, right? Structures 4 and 5 with 2 enantiomeric pairs. Because we have the left and right-handed versions of those molecules. So total, if you're counting that in your total isomer count, you'd have 8 total isomers. So that's about it for this structure, MA2B2CD. And check out my other videos. We'll be going through all these for octahedral isomers, and eventually I'll post videos as well for other geometries as we get through them.